Right, we looked at partial fractions, and when we dealt with partial fractions, the denominator was always a combination of linear and quadratic factors. Now, the linear factor is fine, because we know that's always going to end up being a log situation. But let's look at the different situations when it's a quadratic denominator. Right, we could have difference of two squares. We have a squared minus x squared or x squared minus a squared, which then we could factorise and do via partial fractions. However, there's your standard integral for that. Again, I think it's well worth remembering that to save time. But of course, if you don't remember it, you can always do it via partial fractions and get the answer. You could have the sum of two squares. The sum of two squares is our standard integral for inverse tan. The other situation with quadratic denominators is when we have the square root of the denominator. So square root of a squared minus x squared, well, we've seen that. That's inverse sine or minus inverse cos. But then, so there's these two, which you'll recall that I said were one's worth remembering, again, to save time. If you, do not remember them, then it's done via a trig substitution. You'll eventually get there. Okay, let's just do some examples then. So how do I get it into that form? It all comes down to completing the square in the denominator. So x squared plus 4x plus 9. If I complete the square on that, I'll get x plus 2 squared plus 5. Sum of two squares, inverse tan. So we've got 5 lots of 1 over a in this case is the square root of 5, inverse tan of x plus 2 on root 5. And so tidying that up, we get root 5 times the inverse tan. Here's one with the square roots. But you notice we've got a linear function on top, 3x plus 2. How do I deal with this? I split it into two integrals. Now, the first integral, I want to set it up so it's du on root u. So therefore, I just place the derivative of that quadratic on the top of the fraction. So x squared minus 4x plus 1 is 2x minus 4. Obviously, I can't change the question. So I look at the x's. It was 3x. I've now got 2x. Therefore, I need to balance it out. 3 on 2. That's also going to affect my constant. 3 on 2 times negative 4 is negative 6. To get it back to 2 in the other integral, I add 8. Negative 6 plus 8. All right. So the first integral is now du on root u, which we know is 2 root u. And the second one I can do by completing the square. Now, of course, if you don't recall the 2 root u, you do the first one by substitution. And then hopefully it becomes obvious then when you see that, the u is x squared minus 4x plus 1. Of course the u is that. That was the whole point of setting up the fraction. The second one, I'll complete the square. So I've got x minus 2 all squared. To balance out the plus 1, I need to subtract 3. So first one, 2 root u. Second one, square root of x squared minus 3. That was the log one. So I've got 3 root u. But then we've got 8 lots of the log, x minus 2 plus, and then the square root, it just matches the square root that we had in the question. So square root of x squared minus 4x plus 1. Substitute in for that 3 root u, there we go. So 3 root x squared minus 4x plus 1, plus 8 log, etc., rather than me saying all that. Okay? So split it into two integrals, you handle it quite easily. Something like this, where you look at it and go, hey, whoa, that's not a quadratic denominator. Why am I doing this example? Well, I'm going to turn it into one. So I'm sort of going to do the opposite to what we normally do. Normally, we would rationalise the denominator. I'm going to rationalise the numerator. Because then doing that, I've got something similar to the last example, where I'll split it into two. First one, I'll create the derivative on top, so I end up with the situation, du on root u. The derivative of that one's minus 2x minus 1. So I need to balance it out. I had x, so minus a half. Minus a half times minus 1 is plus a half. I want to get to 3. And so it'll be plus 5 on 2. So of course the first one, du on root u, that was the whole point of making that one. The second one we'll do by completing the square. But again, if you forget about the du on root u, u is 6 minus x squared. Du, surprise, surprise, turns out to be minus 2x minus 1. Again, that was the whole point of splitting the fraction up. Now, got to be careful with this one. Completing the square, but it's minus x squared. So therefore I know it's going to be minus outside the perfect square. So when you expand it out, you get minus x squared. But you now need to be careful with the number inside. So half the coefficient of x. Coefficient of x at this stage is -1. Half of that is -1/2. But I'll need to put +1/2 in this one, because eventually, when we expand the whole thing out, it's going to be multiplied by minus. You've got to be very careful with those ones. So I get x +1/2 squared. That gives me -1/4. I want 6, therefore I need to add 25 on 4. So first one, oh, what do you know, 2 root u. Second one, we have an inverse sine situation. So 2 outside of x +1/2 on 5, that looks a bit ugly. So let's multiply the top out. And there we have it. Minus root 6 minus x squared plus 5 on 2. Inverse sine 2x plus 1 over 5 plus a constant. Now we're getting some good integration. So let's have a look at these ones again. I said it's well worth remembering, and they're quite easy to remember. The way I think of it, I know it's 1 on 2a log, but then I have a look. It's a squared minus x squared. So if the integrand finishes with the x, the minus x squared, then the last thing I'm going to write down is the minus x. So if you think about writing, starting with the numerator and writing, well, the last thing I write down then would be the minus x. So a minus x goes on the bottom, therefore a plus x is on the top. If it's this one where it's x squared minus a squared, it starts with x. So this time when I'm writing it down, I'll start with x. So I'll write x minus a, the other side therefore must be x plus a. And that's how I tend to remember those ones. All right. Oh, you know what that means? Exercise, jolly good fellow.